Thanks. The plushie raffle. So definitely make sure you fill out this check-in form in order to be entered into that. I'll leave that up for a second. And maybe we can drop it in the chat as well. Okay, awesome. So today, the plan for the first half is we're going to talk about what computer vision is. Then we're going to talk about OpenCV in that context. Then we're going to talk a little bit about doing art with OpenCV. We're going to have like a guided demo where we actually run some code ourselves and set up our environment to create some new art based from a picture using OpenCV. Then we're going to pivot a little bit and talk about command line interface tools and why those are important. And then finally, we're going to close out this first section of the OpenCV demo by building a command line tool for processing images with OpenCV. Okay. So what is computer vision? So I pulled this from Wikipedia. It basically says computer vision tasks include methods for acquiring, processing, analyzing, and understanding digital images. So one such task could be identifying, given a set of photos, identifying which are dogs and which are, I guess, blueberry muffins. But yeah, the key here is to recognize those four main like areas of focus, right? Acquiring information, acquiring digital images, processing digital images, analyzing digital images, and understanding digital images. Okay, so why is computer vision important? Well, there's a lot of money to be made in that industry. I have a graph here that shows the market size, and like it's forecasted to grow significantly in the coming years. And it has many different kind of industry applications, from transportation to healthcare to manufacturing to even retail. So you've probably heard of like self-driving cars, right? That's a very common application. But another common and very powerful application is in healthcare in like disease detection, because it requires a lot of kind of content knowledge, right? So for somebody to train and be able to identify things takes a long time. But if you train this model, you can apply it basically anywhere and identify those and save lives. Okay, so let's get a little bit more into the details of computer vision. Generally, we can, or like one way that we like to break it down is to break it down into 3 R's. So the first one is representation. That just means like, how do we represent the world around us? The second one is reorganization. So that's how do we transform like a representation of the world around us into something that we can interpret. And then finally, we have reorganization, which is, recognition, which is how do we interpret or reorganize interpretation of the world around us. So as an example of that, I have 3 images on the bottom. On the left, we have like a photo, kind of like what humans would see, right, around the world, like of the world around us. And that's kind of a representation of the world. The second image here is a reorganized form. We've done some transformations to kind of clear out the color, and we basically only have the edges of the image. And then finally on the right, we're performing recognition, right, where we actually take our reorganized form of the image and like identify which coins have which names and draw a little kind of bounding around it. Alrighty, so getting into those details, here we have an example of like maybe something that you'd see in the real world, right? It's simplified a little bit for this example, but effectively it's just like a Python. So how can we store this kind of image of a Python digitally? Feel free to hop on the mic or drop your answer in the chat. Otherwise, I'll just answer it. The hint here would be take a look at the grid, right? There's a grid on this image. So what we'll see is that like a very common way to do it, like probably the most popular way, is to essentially draw a grid over an image if we don't already have one, and then create an array with the same number of entries, essentially like a 2-dimensional array, kind of like what I have in the top right here. And then just loop through every tile in the grid, and then if it's white, record a 0, and if it's black, record a 1. or vice versa, depending on like how you want to encode it. And what we can see here, like on the top, I have kind of the digital representation of the image on the bottom right. And if you kind of squint at it, you could probably see that like I kind of like tried to highlight it. You can see that it looks kind of like the Python on the bottom, right? We still have that preserved. So something to note here is that like in the real world, right? If you draw a grid, there's a chance that maybe you have multiple colors in one tile, right? So you have to have, sorry, some sort of logic to determine what value you want to put in each tile. And it's not going to preserve the full kind of exact shape of the image, but it can be very close, especially if that grid is very, very large. Another thing that I'll point out is like take a second to try to think about what edges look like in this representation of an image. Yeah, so what you'll notice is that whenever the value of a particular pixel, or I guess like value in this array changes from the adjacent like tiles or entries, we have an edge. So for example, right on the top of the Python's head here, we can see that we have values of 0, but if we're looking for a horizontal edge, we can check the value directly above it and see that those are all ones, right? So we can effectively identify that there is an edge in the image here just by looking at the change in the values. And by kind of building upon that, we can also say like, okay, if we have an edge here, an edge here, an edge here, and an edge here, then we effectively have like a rectangle, right? Or something of that kind of general shape. So we can effectively identify, broadly speaking, shapes using this logic. Okay, so now I've changed the image slightly. Take a second to think about how we can represent this one. Yeah, so what you'll note is that this is, instead of black and white image, it's grayscale now, meaning that all the values are on like a single kind of color scale, but it's obviously not a full color image. So now to do this encoding, instead of using like just on or off 0 or 1, you would probably want to use a scale of values. So assuming we have a maximum of 256 different color values, we can use a scale of 0 to 255, and then just kind of use that same array, same size and everything, except each value now would just be a value from 0 to 255, depending on the color along that scale. And something I'll point out here is that like the image doesn't necessarily need to be grayscale. Like for example, if you think about maybe you've seen like the classic Game Boy, that's more like a greenish hue, but it uses the same logic here, where it's just a single kind of color scale, and it applies. It just uses like a single range of values. Okay, so slightly more complicated. Now we have a full color image. So to encode this one, what we'll see is that we will want to use 3 channels. So essentially, instead of having a single array of values from 255 to 0 to 255, we have 3 of them, one for red, blue, and one for green. And then we just kind of combine the 3 to form a full color pixel value when rendering it. Okay. So now we have, we're still in color, but we have a video, right? Instead of an image. To try to take a second to think about how we can encode this full video as opposed to just a single static image. So what we'll see is that we will use, instead of just like a single kind of set of 3 arrays, we would have 3 arrays for every frame of the video. And then since a video is just a series of images like displayed in sequence very quickly, we would just have one for every frame. Yeah. Okay, so kind of a summary of representation, that branch of computer vision. Largely, it's considered like a solved problem, meaning that assuming we want to represent something that we, like as humans, see, we can do it digitally. Generally, the specific representation will depend on the specific input device that you're using, and you'll choose the input device for the specific use case. So as an example of that, like for example, if you need something, if you need like a car, or if you want to program a self-driving car, you'll probably want something that can like have a very large a large amount of input, I guess. So for example, you can use like a traditional camera. But if you want to program like a very simple kind of uh, like something you do in IEEE or like an introductory electron like EE class, where it just kind of like a little robot that moves forward and backwards, right? Depending on if there's a something in front of it, you can just use a very simple like infrared sensor that has a single single channel of input as opposed to like full color. Okay. So the image is cutting off the texture a little bit, but let's not worry about it. So now let's move on to reorganization. Instead, now, like assuming we can digitally represent our images, the core motivation here is to streamline the process of recognition by performing some sort of transformations so that our representation is very easy to work with and analyze. So typically what this will constitute is both removing noise from our images. So that can be from whatever the sensors we have, or maybe introduced somewhere else in the process, as well as removing any relevant information in the image that we don't really care about for our specific recognition task. So the example we're going to work with is looking at the learn.py Python and then the green one here, and trying to encode a consistent representation so that when we perform a recognition task on them, it's very easy to tell that they're the same on the line, like they're both Pythons. Okay, so yeah, the first kind of example here, first thing that we'll probably want to do, first transformation, is desaturating both of the images. So on the left, we can see we have both of the images, right? They're both in color, so they have those three kind of arrays. And we want to desaturate them, which basically means transferring them from a color image to a grayscale image. And that's what's getting cut off. So on the right, we have the grayscale versions, and then we note that they are represented by a single array of values 0 to 255, as opposed to three different channels. So this operation, all it really entails is just taking the average of the three channels and then recording that value. So you just go through each pixel and take the average of the three and then write it over here. Not too tricky. Okay, next, once we have a grayscale image, we'll want to perform edge detection. So to do that, basically, all we're doing is we're just looking at each pixel and then looking at the pixel before it, either in the vertical or horizontal direction, and then checking to see like what the change of the intensity value was. So here, for example, in the top left corner of the snake, it changes from like purely white to kind of like a mid-level gray. So we would expect like kind of a mid-level degree of line here, right? And then we just do that for the entire image, every pixel in the image. So here we're effectively trying to get rid of the ambiguity of like the different colors in the middle of the image, right? By just looking at the edges. And now finally at the end, since our image is still a little bit messy, right? We have these kind of lines in the middle for like whatever the shading was, I guess. We can perform thresholding, where all we're doing is just kind of setting like a minimum threshold value, and then we are just cutting off all the values below it, right? Just setting them all to 0. And now here we are basically left with a black and white image again, like where all the values greater than 250 are set to 1, and all the values less than 250 or less than or equal are set to 0. And now we can see both the encodings are exactly the same. So obviously reorganization is going to kind of vary by the specific task that you're trying to do. Some other examples that you can see of like a starting image that could make it be a little bit more complicated, or if we scale the image up, for example, this one is 2 times as large, as you can see by the grid. This one here has noise introduced. So for something like this, you'd probably want to blur it before you do any additional transformations. And then this one here on the right has been flipped, but it's also been kind of changed a little bit, right? The snake, the mouth is not, but the tongue isn't out. So in that case, you may need to use a slightly more involved recognition like model or solution, I guess, whatever you want to use there, than just kind of directly comparing the two and seeing if they're identical, like we were able to do in this case. Okay, so some of the core goals, like from those examples that you can see, are blurring. There's a variety of ways to do it. If you're interested, check out the four that I've listed here. Edge detection. Essentially, at the end of the day, it's just comparing the change in intensity, but there's a variety of ways to do it again. I've listed a couple. You can perform corner detection, which essentially leads into like key point detection is what they call it. And then you can detect objects based off that. As well as depth perception. If you have multiple cameras, you can kind of rederive like how deep something in the image is. And then panoramic stitching, kind of like what your phone does when you do a panorama. Takes multiple images and then stitches them together. Okay, so let's move on to the last R, which is image recognition. So yeah, the basic goal of image recognition is analyzing and understanding digital images. Once we have a representation of them and we've reorganized it into a form that's easy to interpret. So generally, it'll involve leveraging some sort of deep learning models. Convolutional neural networks are very common here, as well as recurrent neural networks or RNNs. You'll see for like video streams. And generally, these are pretty compute intensive, right? Because they have to run these large models, especially when they're training. So you may want to use cloud compute to do so. Okay, so I'm going to briefly talk about some of the tasks under recognition, and then I'll let Sam touch on that when he gets to his section. But yeah, generally you can divide it into 5 different task areas or 3 main ones. So first is classification, where you take some sort of image input and you assign a single tag to the image as a whole. But so here you can see they're assigning on the far left cats to an image of a cat walking. And then a little bit more complicated than that is classification with localization, which is in the middle here, where they're not only assigning a tag, but they're also drawing a bounding box around the specific thing that they're trying to label, right, the cat. And then more involved than that generally is what's known as semantic segmentation, where they basically segment the image into different sections and then either tag all of them or tag one in particular, right, the one that's most interesting. That's the second one here on the left. And then finally, you can kind of do each of these if you have even like in images that have multiple targets. So on the right, you can see they're doing one that they're doing a picture that has 2 dogs and a cat. And then on the right, same thing, but they're doing segmentation instead of localization and classification. Okay, cool. So any questions on computer vision as a whole before we move forward? Again, feel free to hop on the mic or drop in the chat. Okay, awesome. So let's go on to what OpenCV is. So OpenCV define themselves, as the world's biggest computer vision library. They are an open source library, which means anyone can technically contribute to them. And they have interfaces in C++, Python, Java, and MATLAB, if you're so inclined. The reason why we're using Python is because this is learn.py, obviously, but also Python is very intuitive, and it's very easy to get installed or get things set up and get things running very quickly. So OpenCV also has very widespread usage among like many industry leaders, which makes it a great choice to familiarize yourselves with if you're interested in working at any of those companies. Okay, some specific use cases where you may want to use OpenCV are for image thresholding, doing any sort of like kind of traditional transformation on the image, like for example, rotating it, translating it, that kind of thing. Edge detection, like we talked about before. You can also do contour detection, and then any general image processing. So like if you want to draw something on an image or parse it to try to like identify something in particular. And then you can also do image segmentation and object detection. Okay, so I'm going to kind of throw you guys in at the deep end here, and then we're going to walk through this code to try to get our hands dirty with like what OpenCV actually is and what it actually looks like. So on the top left, we can see a little red box there that shows how to install OpenCV. Fortunately, if you have Python, it's just a single command. So assuming you created a virtual environment and activated it, just for best practice, all you need to do is run that command at the top to install OpenCV. And then what we'll see here is if you run the code in the bottom left, it will basically create this window that we can see on the right, where it's rendering the learn.py snake and then drawing a blue bounding box around the snake. So yeah, you don't need to run this on your own computer or anything. This is just to kind of get your hands, get familiar with what OpenCV looks like. So let's go line by line and see what this code is doing. The first line here is just importing the library, the module that we installed. And the second line is calling this image read or image read function. And then we're giving it the location of the image to look for. In this case, it's the learn.py image that we have alongside our code where we're running this. The third line here is calling the rectangle function, and it's taking in the image to draw the rectangle on, as well as coordinates, like for the corners of the rectangle, the color, so in this case, it's just blue, and then, I forget what this last parameter is, but if you look at the documentation, you could see what it was. But effectively, what it's doing is it's drawing this rectangle on the image. And then finally, we can see that we have this image show function that's actually telling OpenCV to create that window. Right? We can see it has the name display window, which is in the top left or top right. And then we're passing in the image to use. And then here we call the wait key function, which basically tells OpenCV to wait a particular number of milliseconds, or if this is 0, it'll wait until a key is pressed. And then finally, we have at the bottom here, destroy all windows, which is going to destroy anything that's created with image show. And it's just best practice to include it at the end to clean everything up. Okay, any questions on this code before we move forward? Okay, awesome. So yeah, some of the OpenCV key functions that you want to know. Hold on 1 second. I'm going to switch over my speaker. Okay. Let me know if you guys can't hear me or whatever. Okay. So the top here we have the image read function that we talked about, right? It takes in the path to the image, as well as kind of some conditional or optional arguments for the specific like way to parse it, whether it should be in color or grayscale. We have the image show function, which tells OpenCV to actually display the image, and is generally used with that wait key function that we saw. And then we have the image write function or invite that we didn't show, but it's very simple. Basically, it just takes in a path to write out the image, and then the image to write out, and then it'll just save that image like on your computer after doing the transformations, so you can actually have it and share it or do whatever you want with it. Right. Another thing that I'll note is that OpenCV also has many more functions for reorganization beyond, like for example, that rectangle one was sort of reorganization. And then as well as for recognition that Sam will talk about later on. Okay, so let's get on to actually working with OpenCV now that we've talked for a little bit. Yeah, basically, one thing that you can use OpenCV for is creating digital art. Sorry about that. So we can see on the right here, the top left image of the images on the right, we have a picture of Royce Hall. And then we have 3 additional kind of transformed images of that in like different styles. And these are all things that you can do with OpenCV, and we're actually going to do together. So why would you want to use, why would you want to create digital art? Well, so as the world kind of like transitions to more and more to use leveraging technology for everything, all art more or less is saved and shared digitally nowadays. And most modern tools, like for example, if you're doing photo editing, I guess like Photoshop and Lightroom,
leverage either OpenCV or other proprietary libraries that are like in the same vein to do most of the kind of traditional image transformation tasks that you'll see, like if you're cleaning up an image or whatever. So the problem with using those though is that they're quite expensive, right? If you're not on like a specific account that's paid partially for you, you're probably gonna have to shell out like $60 a month. And yeah, that makes us sad. So the alternative is to use OpenCV, which is since it's open source, right? It's very, very cheap. It's free. And it lets you become a meme lord, meaning you can like do this image transformation on the right, where we take just a regular photo and we can deep fry it. You can understand the implementation behind everyday kind of art, like how it's made, to have a better appreciation for that and like talk to folks about it, as well as understand like how to automate a transformation process. So if you, for example, want to transform like all the photos that you have, like maybe you went on a trip, right, and took like 100 pictures. You don't have to do them all by hand. You can automate that process and just run like a single Python script, and it'll do it for you. Um, and then you'll also get a stronger understanding for the foundations of working with OpenCV and computer vision, so that if you want to do some cool recognition tasks, you have a strong knowledge. Okay, so let's look at some examples of like how we can actually do this. So I think this is in this image on the right, top right, is in France. And you can see that the top right is just the regular image, and then the bottom right kind of looks like it was like a watercolored painting. And OpenCV actually has like a single function that you can do this transformation with without any hassle. So what that code would look like is first importing OpenCV, reading in the input image, which is the second line here, and then finally in the third line, just calling that stylization function. So to do this, you pass in two parameters with like these this is the meaning behind them. I won't talk too much on that, but if you're interested, you can look at the documentation. Okay. Another example you can see is like kind of simulating sketching digitally. So for this one, you just call the pencil sketch function, and then you can plug in like there's two same parameters that have the same meaning, and then there's an additional parameter here for the brightness of the output image. And what you'll note is that this pencil sketch function actually returns two values, right? As a tuple. So we can see that we're using the first one as the image. So what is the second one? Actually, I don't have a slide on it, but you'll note if you run this locally, you can see that the second image is actually just a color sketch. So they're both different versions of the sketch for that you can use for different things. Okay. We also have oil painting. So for this, you just call the oil painting function. Again, very simple, similar to before and very simple. And then here we have a slightly more involved example where we're simulating pointillism, which is a specific art style. So for this, you'll probably need to write out like maybe like 20, 30 lines of code to do some like specific image analysis and draw these like specific shapes on the image. We have an example of it, so I'll show you what that looks like. But it's a little bit more tricky than just kind of using the standard built-in functions. Okay, so let's go ahead and actually write some code now. Right, we've been talking for half an hour or so. So what will you need? As Hannah and Sneha mentioned at the top of this, you will need Python. Ideally, it's 3.7 or later. I believe that's the earliest version that OpenCV supports. Make sure that when you're installing it, you check the box to add it to your path environment variable. If you haven't done that, you're probably gonna have to do it manually. And then it should come with pip, which is like the default Python package manager. And that's just what we'll be using to install OpenCV. And then you'll also need some sort of text editor. We recommend VS Code since it's pretty straightforward to get started with. And that's what we'll be using in the demo. Okay, so without further ado, let's go ahead and get started. So let me, yeah, the directions are on the slides here, but I'll be doing it live. So no stress there. So I'm going to open VS Code. I guess I can do it this way. Visuals, video, code. Okay, you full screen this. And then now we'll want to kind of open up a folder that we're going to be using for our project. So I'll click open folder. And then, I mean, you can just choose wherever you want. I'm going to put it under hack, probably. Just create a new folder here. So learn.py live. Okay, select folder. So now we can see that it's opened up the folder, right? But we don't really have anything in it yet. So let's go ahead and click this terminal button and then new terminal to open up a terminal. And we can see it is in the folder that we just created, right? It has that file path. So what we'll want to run is the command python -m venv this. Oh, sorry, my phone charger is a little bit stuffed. It keeps opening that. Like this command. So what this is doing is it's saying run Python. This -m is saying like basically run a particular module, and then we're passing in this virtual environment module. So we're saying run the virtual environment like module, and then this is the name that we're passing for our new virtual environment. We're effectively saying call it .vn and then create it in like the current folder. So this will create a new virtual environment for us. We can see it's already kind of done it here, right? It has a folder, then it's still processing, adding whatever it needs to. So we'll let that run for a second. While that's running, we can create a new file here. Oh, okay, it finished. Awesome. So now it's created that, but it's not using it yet. So what we'll need to do is we need to actually activate it. So on Windows, I believe the command is. Oh, a second. And the Mac command should be on the slides as well. Okay, so now that we've activated this, we can see that it's like prefaced here by the virtual environment, so we know that it's actually using it. And then we will actually go ahead and create a new file here. Let me zoom in. So I'm going to call it requirements.txt. So this will be where we just kind of keep track of the dependencies for our project. And we're going to add OpenCV Python, and I think this is just for more experimental stuff. That's the difference, I believe, but not 100% that's certain. But we'll need both. Okay, so now that we have that, let's go ahead and run the command pip install -r, which means we're installing requirements from a requirements file, and then we pass the where the file is. So like that. You don't technically need this // You can put it if you want. This is just saying like use the package manager, install requirements file, and then passing in the name of it. So we can see it's installing this. And this may take a little longer if you haven't installed it before. Okay, so we'll let that run. While it does, let's create a new file here called main.py. Okay, and yeah, feel free to stop me if I'm going too quickly or something doesn't make sense. So what we'll need to do here is, actually, before we write this code, let's go back to the slides. And this image here, we have to down, right? Because we need to have some sort of image to do render and transform. So I'm going to just open this up. Okay, hold on a second. Things have shifted around a little bit. We'll just look under OpenCV art here, OpenCV demo, template, and then images, and then download this one. Download. Okay, awesome. So I'm just going to copy it. And then if I want to paste it in here, let's see, paste. There we go. Awesome. So now I have the image. I have a requirements file. I've installed the requirements. So now let's actually write some code to render the image. To do that, first things first, you'll probably want to make sure that you're using the correct interpreter. So here on the bottom right, you can see it is using like the one that I created, right? You can see it's using like .vn in the current directory. So then if we do write the code imports open our cv.2 like this, it'll work, right? It won't give us any warnings. So what we can do is write the code image equals, and then leverage that im show function. We need to provide the path to the image. In this case, it's in the same directory, so ucla.gpg or jpg. And then we can write like this. Again, nothing new. We're just calling that image show. Sorry, this should be and then wait key, just like before, and then cv2.destroy all windows. Okay. Any questions on the code that we've written so far? Okay, so to run this, what we can do through the command line, well, first we can just type in ls to make sure like everything is consistent, right? We can see that these files are the same that we're seeing here. So it is in the same folder, just like we see. And then we can type in Python main.py. So we're just saying run main.py with the Python. We can see, voila, it's creating it's displaying our image, right? Reading it, displaying it. So we close this. We've effectively created the code to read the image, but we haven't done any transformations, right? We haven't done anything artsy. So let's go ahead and do something. We can basically let's do a the oil painting thing. So for that, we just call just like off the slides, oil painting. So here we can see that just hovering over this oil painting function, you can see the first parameter is the image, the source. And then there are like two other parameters. I have details on the slides for what they mean, but I'm just going to use the default values that we were using before. And then if I rerun the command, I just pressed up on the arrow key to rerun the same command. You could also type it out. Yay, we can see we have an image that has been kind of oil painted. Okay, great. So now let's do something a little bit more. So I'm going to do this, and then we can let's rename this oil, and then we'll just copy this code and do a couple more transformations just to show that it actually works. Right. So I'm going to paste this code here. We're going to try change this to what's the function called? Pencil sketch, I believe. And then just change these parameters. So we can write sigma r equals 0.15, sigma s equals 60. And remember, if we hover over this, we can see the return type is a tuple, right? That has two values. So it's returning the black and white one and the colored one. So we'll call this so sketch black and white, and then sketch color. And then what we can do is something like this, where we're displaying the black and white one, and then we're displaying the color one. Okay. Let me know. I'm just going to pause quickly. Everyone's still following? Okay, awesome. Let's go ahead and run this. You can see we have our oil painting one here. If we close it, we have a sketched one. It looks a little dreary, but we do have it. And then we have a colored version. Okay, awesome. So now we've done kind of a couple different transformations. They're all built-in ones. But let's kind of try to see how we can actually build upon this to do something a little bit more complicated. So I am going to go back to the slides. Okay. So yeah, originally if we were in person, now we would break off into like a work session and kind of help you guys out to design some more custom art transformations for yourselves. I have a bunch of them listed here with links to guides. I think personally, I would want to try out this ASCII-ifying one, and this low poly thing looked pretty cool. But if you're interested in any of the other ones, definitely check them out. We're gonna move forward though for now, and then at the end I might show the completed demo so you kind of know what some of them do. Okay, so moving forward, let's pause slightly and talk about command line interface tools. And then we'll kind of get back to OpenCV. So if you've worked with a computer before, which I'm sure most of you have, if not all of you, you probably are doing it through a graphical interface, or like GUI is the term that you might hear, especially if you have a Windows computer or like a Mac. Generally, if you work with like a Linux machine, though, like for example, if you have to connect to CSNet to run some code, or whatever, you will do it through a command line instead of like a graphical kind of like click, drag, and like move your mouse and click interface, right? So CLI basically just stands for command line interface, and effectively it's just like a terminal, right, that you interact with. So some of the strong advantages of using a CLI over a graphical interface is that you can streamline automation. Specifically, like you can tie a bunch of tasks together directly. So for example, if you want to process an image, right, you can process the image and then copy the image and then send an email with the image very easily with just like a single command, instead of like if you have to do that through like on a Windows computer without access to the command line, that would be sort of a nightmare. It also helps with a faster runtime because it doesn't need to render the like visual display. And then generally there's like more customizability and control through a CLI, because the developers don't have to implement like a button or like something to display for each custom variable command. So some disadvantages, though, pretty obvious one is like there's a steeper learning curve, right? There's a reason Steve Jobs didn't have the Mac, just use like a terminal, right? And then also if you're doing some sort of analysis or like need additional accessibility, generally like CLI obviously isn't going to be as supportive for that. So as an example of like what interaction through a CLI might look like, I have an image here on the right. This is using a Linux distribution called Ubuntu. So basically all the like common Linux commands that maybe you've seen, maybe not, are can be run here. So we can see at the top, somebody's running this pwd command, which stands for I believe print working directory. So we can see it's displaying the directory here, right? Which is, I guess that's where the current command, like the terminal currently is. So typing in ls, which just lists the current files in the current directory. So we can see there's a folder here, and then there's a file. And then the cd, and then a name, basically just changes the directory. And then like basically goes down a level, like a folder level. Right, so they're using this John directory. And then I guess this history command displays the last commands run. So we can see them here in a reverse chronological order, I believe. Okay, so CLIs are fine, right? Or CLI tools are fine in general, but like what about developing CLI tools with Python? Well, like one way to do it is to leverage Python's arg parse module, which, like as the name implies, it just helps you parse arguments. It's not the only way to do it, but it is a very kind of straightforward way, or relatively straightforward way to do it. And I think CS35L uses argparse, so it's good to kind of have some working knowledge of it, either ahead of time or afterwards. So we're going to kind of be going through a quick example here of a program called program.py that either returns the sum or the maximum of a list of integers. So it's a little cut off here, sorry, I apologize for that. But we can see in the example below, we're running program.py and we're giving it the list 1, 2, 3, 4. We're telling it to sum, and we're telling it to repeat 3 times. And then we can see in the next line, right, the output is the sum of those 4 numbers, so 10, and then it's just displaying it 3 times. Another thing to note here is that there are kind of different types of arguments that we can give to a program, and there's no like fixed rule for these, but there's best practices to follow. So generally, we can see that there's a notion of a positional argument, which doesn't have a name, but it's so it's basically based off the position of where it is, and then it's kind of stored. There's a notion of a flag, which only has a name, and it's either like present or not present. So based off of whether it's present or not, it'll do one thing or a different thing. And then finally, you can have a named argument that has a name and a value. So generally, it would be the name and then a space and then the value, or some sort of white space and then the value. And then lastly, what I'll note here is that you can have like an argument in a long form as well as like a shorter form. So generally what you'll see is that if you have these two dashes, you're gonna like have a longer, like just more than a single letter. But if it's just a single dash, you can have just a single letter here to kind of keep things clear and concise. Okay, so let's go through, look at an example of arg parse. I know there's a lot of stuff on the screen, so let's just break it down very simply. It's the same program, it's just the implementation. So again, we're just taking the sum or the max of a list of integers. In the red box, we can see the command that we're running. So in this case, we are giving the list and we're not providing that sum flag, right? And then we'll expect the output then just to be the max, which in this case is 4, right? And we see that 4 is what's outputted. In the blue box, we have the internal representation of the parsed arguments. So if we're just looking at the red box, we can see that we have the list 1, 2, 3, 4, and internally we store that in args.integers, right, as a list. And then args.op is set to max because we're not taking the sum, we're taking the max in this case. So if that part makes sense, let's look at the code on the left. And we can see the first line here is just importing arg parse. The second line is creating an argument parser. So effectively, this is what's going to store like what we want, like the kind of names of the arguments that we want, and like any conditions that we have on them. And then we're basically saying in this argument parser, we're calling this add argument function to add an argument for the integers. So we're saying the name is integers, right? If we look at the blue box, we can see that's where the list is stored. And then the type is integer. And then this nargs is a little bit confusing, right? What does plus sign mean? Well, if you look at the documentation, plus sign just means that it's going to like store it in a list format like this. I believe there may be some other condition on it. You'd have to check exact documentation. But the important thing is that it's storing it in a list. And then this fourth line is doing something similar, right? It's adding another argument. It's saying that this is what it should look for, right? Dash dash sum. And by providing this dest, basically saying store it in op, like this op word. And that's why we can see down here, right? It's storing args.op. In this case, as max because sum is. And then here we're saying the action is store constant, meaning it should store some sort of constant value in op. The const value it should store is sum. And then the default value is max. So it's either going to be sum or the default value, which is max. And another thing to note is that because these are the sum and max, these are actually built-in functions in Python, which is why they're yellow. So that's why down here in the bottom 2 lines, first we can see we're parsing the arguments by calling parse args. So that'll basically make it so that the arguments are actually assigned into args, right? Whatever's returned here. And this args is just a dictionary. And then finally at the bottom, we're calling this operation as a function. And then we're just plugging in the integers, the list. Okay, so that was a lot. Let me know if there are any questions on that before we move forward. Okay, so this is just another quick example where we are, instead of taking the max, we're taking the sum now, right? Dash dash sum. And all that's changed is that this output value is 10 now, and then this operation is sum instead of max. Okay, so some of the key arg parse constructs to be aware of are the argument parser, which is like you'll have to create it before you actually add any like you're basically creating that and then telling it what to look for, right? This add argument function, which has a lot of special kind of configurations that you can add, but also a lot of very simple ones that you can just use by default. And that's just telling the arg parser like what arguments to look for. And then finally, at the end, once you've added the arguments, you call this parse args function, which will actually do the parsing and store the results in a namespace, or effectively just a dictionary. And then you can just access the elements with the operator, just like we saw, right? Integers that args.integers, args.op. Okay, cool. So obviously that's not that's not computer vision, right? So why are we doing this? Well, let's go ahead and tweak our code to make it more customizable and make it actually like somewhat useful. So I'm going back to our code here. What we'll do first is create a new folder called images, and then move this image into the just to keep things clean. We'll also create a new folder called output, not like that, just so that we can actually save our output images. Okay, so next what we'll do is we're going to try to use argparse to make it so that instead of running all these transformations, we just run a single transformation, right? We can customize it through the command line. So what we will want to do is let's just do it up here. So we can say import argparse. It's part of the standard library, so no install is necessary. Then we can do parser dot argparse dot argument parser, just like before. And like if you see me like autocomplete, I'm just pressing tab because it's suggesting it. And if I press tab, it'll do it. And then we can run parser dot add argument, and then we're going to just say in this case, let's start off by something simple. We're just going to take the image path as our first argument. So we're going to say path. So that's the name, and then we can say default equals images slash UCLA.jpg. Jesus. So this is just saying look under the image, like this is the path, right, for the new target image. And then we're going to say nargs equals question arg. So that means if there's a value given, use it. Otherwise, use the default, basically. And then here, we don't want to do that anymore. So this is to do. I'll get to that in a second. We will want to call parser.parse args, and then store the result as args. Just another variable. So finally, we can change this to say args dot, and then we want to use this name, image path, right? Because that's where it's going to be stored. So now I'm going to go ahead and comment this out. On Windows, it's Control / to do that. Save this, and then I think we should be okay to run this. Basically, all it's going to do is either look for an image path that we give it, or use this default one, and then read the image, do the oil painting. So let's open up a terminal again. Yeah. Okay, I'm gonna just use the same one that we were using before, that was still there. And then we can run the same command. We see it's working, right? And we can also run the same command and give it a parameter here. So let's say /images/. So here I'm specifically specifying the image to use, right? And we can see again, it's working fine. It's using that input. If I, for example, move this image out here and run it. So I'm going to change it to now say, look in the current directory for the image. We can see again, it is working and finding that image in the correct spot. If I run this command, yeah, it's going to say it didn't find it, right? Because it's not in images. Okay, so now we've done some simple parameterization, but like what's the big deal, right? So let's do something a little bit more complicated. Let's add a parameter, parser.add argument, for whether or not it should display the image. So we can call this one display, like this. We will store it in display, and action equals store true. So what this means is that it will either, like if this action, if you look at the documentation, it's very well documented, or it's very well written. So if you look at it, it'll tell you that the different options for action, one of them is store true. And what that means is that it's going to store either true or false in this args.display variable. It'll store true if this is present and false if it's not. So very easy to work with, like very easy to create a flag. So what we will do here is if args.display. You can add like an equals true here if you want, but you can leave it off as well because this is just saying like this will only be true if the value is true, right? And then I'm just going to do that, meaning if we need to display, then display. There we go. Okay. So let's save this and try running it again. And you can see, well, it skipped over this, right? And then it destroyed all the windows, which was not there. So if we do this though, so now we're including the flag, we can see it creates our window. Okay, great. So now let's get to the thing that I mentioned before, right? Where we're actually kind of parameterizing which flags to use, which transformations to use. So to do this, one way to do it is basically to, I think the cleanest way, in my opinion, is to create an array here. So we'll call it valid operations, right? And then we're just going to give it the different names of operations that we want it to do. So we can say, in this case, what do we have? We have oil painting. We'll have that as one. We have sketching. So we could say sketch. And then we can also do color sketch, right? So those are three that we've implemented. And then what we can do here is we can loop through our array. I'm going to say for op invalid ops. And then here we're just going to say, basically add an argument. I'm going to move on this. Add an, like in here, we're just going to say add an argument for this operation, right? That's effectively the logic that we're doing. So let's write that out. What we can say is something like this. So I'm going to use an F string, which basically means if you use these curly braces, you can plug in a variable. So if I do something like this is saying if somebody types in dash dash and then whatever the operation is, so like whether it's oil painting, sketch, or color sketch, like that's the particular kind of string that will be rendered here. Then let's set the destination to the operation. And then we can do action equals append const. And then const equals. So sort of complicated here, right? These last two, what is going on there? So this is saying this action means append whatever this constant is to the destination. Let's change this slightly. So what this is going to do after parsing, if I write something like this, is it's going to say this args.ops will be an array of operations. And then this is just going to say append basically the specific operation to arg.ops if it's provided. So let me show you what an example looks like, and hopefully it will make more sense then. So if I want something like Python main.py dash dash something like this. Sorry. Right, so here I'm basically giving it sketch and color sketch. What this parse args function will do is it'll see, okay, I have a sketch, so let me append the operation. Remember, that's just sketch to ops. And then it'll also see that it has color sketch. So it'll append that to ops as well. Right. So both of them will be in this array. And that'll let us specify multiple different operations. Like if we want to do two operations on a single image, now we can do that, as opposed to just a single one. Okay. So now that we actually can parse this out, right? Let's do this. We can just say print just to test. I'm going to comment this, or actually we can leave that. So I'm just going to print out the operations, right? If I run this code, we can see, yay, we have the sketch and color sketch. So if I remove that, now we actually need to make this code, tweak the code so that it actually does the specific transformation we want. So because we have a list of transformations, I'm going to use a loop. I'm going to say for operation or op, I guess, in args.op. So this is saying loop through the operations in op, and then sorry, ops, I should say, because remember that's the name we gave it. And then the logic here is just like do the transformation, right? Whichever op it is, do that transformation. So we can use like if you want to use a case statement, you can. We're just going to go with if statements. There's something simple. So if op equals what do we have? Oil painting. Then obviously oil paint. Right. So I'm going to change this slightly. Say else if equals sketch. So I'm gonna remove this line because we moved it up. Uncomment this for now. Copy this line over, paste it in here. So this is gonna do the sketch, right? If we tell it to sketch, we want the output to be in this image variable. Actually, let's do it this way. So the reason I'm doing it this way is so that we still have the regular image, so that if we do multiple transformations, we're not overriding it. So in this case, remember, sketch is just the black and white one. So I'll do this, and then the convention in Python is just use an underscore or underscore and then some sort of name for things like variables that you're not using anywhere. So I'm just going to do that, and then lf equals color sketch, and then this underscore put. So now we have the color one, and then we can get rid of all of this, but let's leave the display logic that we wrote. We're going to move it up into the loop. This is just going to say if display, right? It'll actually display the output, and then we should be output. Okay, so I think we should be okay here. Let's go ahead and rerun the same code. Okay, and we see it didn't do anything. Well, it ran, but it didn't display anything because we didn't include this display flag. Okay, awesome. So we see we have the sketch here and the color sketch, and then it's done. Okay, awesome. So now let's also do uh, let's make sure that it's actually saving these images so we can use them. So what we can do is we can add a bit of code here. So effectively what we need to do is call this imWrite function, right? And then we need to give it the output path. So, and then the output, right? The actual image to render. But what do we want the output path to be? Well, let's write that. So we'll probably like a very simple way to or common way to do it is just kind of look at the name of the input image and then base it off of that. So we're gonna do something like this. File name equals. So here I'm getting the image that's like this is the image path that's given to us, right? I'm reading that in, and then I'm calling the built-in split function, like string split function, on dot, so that we can get rid of this dot JPG at the end, right? So get the first after it splits in the dot, we're just getting the name here and whatever comes before it, and then split again on the slash, and then we just get the last element. So if you don't follow this logic, don't worry too much about it. Effectively, we're just getting the file name. And then finally, we can use another f string here. We're just going to say, write it out to the output folder, file name, dash, op. So this is whatever that transformation that we did was, right? And then we can just say dot, either PNG or whatever extension you want, right? Or you can make sure it has the same extension with similar logic, up to you. But yeah, let's go ahead and do that. We'll remove the display flag. If we open up this folder, we can see, yay, we have both of those files. Okay, great. So that's kind of more or less the end of our guided demo that we're going to do. What I will quickly show you guys is the GitHub repo does have like a completed version. So if you go back to the repo here, I will merge this into the main branch after this. But if you switch over to this complete branch and look at the OpenCV art folder and go into this CLI art complete, and then learn.py, and scroll down a little bit, you can see that there's a variety of different kind of transformations here, including deep flying that we talked about, pointillism, right? And if you want to see how these are implemented, you can look under the respective folders for the ones that are like not built in. And then up here, you can see that there's a little bit more parameterization. And if you look back at the slides, we have some suggestions for things that you could do to build on this if you want to like add it to your resume or whatever, right? Just showcase it. So yeah, definitely check out those links if you're interested, and feel free to kind of drop questions in the Discord or whatever. We can help out with that. Okay, so with that, I'm gonna pass it off to Sam, unless anyone has any questions, to do the part about recognition.
All right, thank you so much, Satyan. That was an amazing demo on ArcParse. I feel like now I know so much more about ArcParse than I ever did. And so that's like, now we're going to, sorry, move on to facial detection, which is a aspect of OpenCV. So let me present. And if you guys are following along in the previous half, just keep your Python environment open. And we're just going to install more dependencies into it. So let's get started. Cool. So before we jump in to what is facial detection, I think if you're doing facial detection in computer vision, some good libraries to know besides OpenCV are scikit-image, also known as skimage, as well as image.io. These are used to do image transformations like we saw. And then Pillow is another imaging library. MediaPipe is used for doing computer vision tasks on video data. And then Tesseract is used for OCR. And then also OpenCV is an open source computer vision API, but there's actually many others that you can pay money to use that are arguably better at the different tasks that you're trying to do. So if you are interested, just feel free to check some of those out. But let's talk about the types of computer vision tasks and then what we're going to be talking about today. So there's many different types of CV tasks, as Satyan said, so I'm not going to go into too much detail, but all of these you can do using OpenCV. Today, we're going to be doing object detection, specifically facial detection. So facial detection is just a subset of object detection. How object detection works is that the algorithm will identify a bounding box for the object, and if there are multiple bounding boxes identified, the one with the highest overlap will be selected. The bounding box will be defined by the basically the top left-hand corner, and then the width and the height. Cool. So you can do a lot with object detection, not just facial detection. But we're going to be focusing on facial detection today. So there are many different techniques for object detection. A lot of them, that the best techniques nowadays use deep learning, but one of the easiest techniques that you can use is HAR cascade classifiers. And this technique was probably the most foundational object detection technique that was that first came out, and it's still used widely today because it doesn't require a lot of data. So you can run it locally on your machine, which is what we're going to do. And it's also known as the Viola-Jones technique. As you can see in this graph, it came out in 2001. Nowadays, the more powerful techniques are split into two categories. Both are deep learning techniques. One is the one-stage detector, and then another is a two-stage detector. I won't go into the details of the model architecture for those, but we will actually talk a little bit more about how you can implement those as well. But when it comes to the hard cascade classifier, which we're going to use for facial detection, um, it's useful to just have a good overview of how this algorithm is going to work. So what we're going to do is split the image into multiple different pieces, and then we will also have these features labeled as letter B, which are HAR features. Um, Basically, how these work is they are an overlay that um, the white parts of the features will multiply the pixel values in that region with like a high value, and then um, it's specifically designed to capture features that are uh, going to be inside of a face. So, for example, faces are assumed normally to have two eyes, a nose, and a mouth, and so the hard cascade algorithm is kind of hard coded to detect those things. And that's why it's a classical machine learning algorithm where we're going to use a bunch of weak decision trees. Each one is going to be trained on a specific feature of a face, like, for example, detecting a nose or detecting eyes in the face. And then they'll be turned into a strong classifier using AdaBoost. And all of these things will be cascaded, where each feature of the face is detected first. And then if, for example, two eyes are detected, then it'll move on to the next cascade, which will verify whether a nose is present. If one of these things isn't present, it'll immediately break out of the cascade, and that way it saves the runtime from having to check all the features of the face. But you'll also see that this can cause issues if you're obscuring your image, um, and that's why deep learning techniques are normally better in terms of accuracy. Great. And just for a background refresher, if you guys, sorry, if you guys did not take M146, AdaBoost is just an ensembling method where the main idea is that you'll have a bunch of weak classifiers, in this case, decision trees, where each classifier is just going to determine, for example, is there a nose, is there not a nose, based on the HAR feature that we kind of like overlaid on top of the image at a specific point. And then they're weak classifiers because most of these classifiers probably only achieve a little bit higher than a 50% accuracy. But the AdaBoost algorithm will identify the spots in the image that cause the classifiers to perform poorly and then specifically train harder on those areas so that in the end, it can weight the classifiers according to how accurate they are and then generate a very accurate classification model. So basically, that's kind of the background behind hard cascades. But without further ado, let's go ahead and get into the code. So in OpenCV, and you may be wondering, by the way, like, why are we learning about hard cascades if they came out in 2001? And there's like so many of these better algorithms out there. But you'd be surprised that how like frequently hard cascades are still used today just because of how like accurate they are despite not needing a large amount of training data or like GPUs or any sort of computational energy to run. Okay, so as we learned in the previous part, um, thank you, Sayan, for introducing basically most of the functions that we're going to need to know today. So hopefully you should be familiar with like CV-imread. This is what we're going to do to read into our images into our Python environment. And as we said before, in OpenCV, all images, when you do an imread, are converted into blue, green, red. So just be aware of that because most algorithms want to accept like a red, green, blue image. So you'll have to convert that to the appropriate encoding using this tool called cv2.convertColor. In the second parameter, you just pass in the constant of what type of encoding you're converting to. In this case, it's converting to grayscale because HAR cascades specifically will detect objects on a grayscale image. So we're going to take our image, convert it to grayscale using this function right here. And then we're going to pass it, we're going to create a face classifier. Great thing about OpenCV is that it already has all these pre-trained classifiers that you can use. This link right here in the slides, you guys can look it up. It has classifiers for example, detecting eyes, faces, cats, all sorts of objects. So just load the classifier that you really want to use. The way you do it is that you do cv2.cascade classifier. That basically just means a HAR cascade classifier. You're going to do cv2.data.har cascades because that's the folder where all these different XMLs that define each already pre-trained model is stored in. And then you're going to type, the name of the model that you want, which you can find at the link inside of this slide. So today we're going to be using the frontal face classifier, which is already pre-trained to detect faces, specifically faces that are facing toward the camera. So if I turn away, it shouldn't work, unfortunately. But that shouldn't be too big of an issue for what we want to do today. So once we create this classifier, also sorry, in the slide, there's a typo. The last line should say face_classifier dot detect multiscale because it is the same object. But we're going to basically run it on our grayscale image, and then it'll return to us a list of rectangles that define each of the faces detected inside of the image. Cool. So we're going to be using VS Code today like we were earlier today, but I want to do things inside of a Jupyter notebook. So if you guys don't have the Jupyter extension installed in VS Code, please go ahead and go into the VS Code extensions area and install the Jupyter extension so you can run Jupyter notebooks inside of VS Code, and also show you guys how to do that in a second as well. Cool. Oh, and let me just give a brief rundown of Jupyter Notebooks in case if you guys, some of you are not familiar. Essentially, they're just an interactive runtime environment for Python where you can run different code chunks at different amounts of time, different times. They're divided into cells. It's very similar to R Markdown if you've used that before. And Jupyter Notebooks actually can also run R and other languages beyond Python as well, but mainly they're used for Python. Cool. Right, so before we get coding, I just want to quickly review a bunch of OpenCV functions so that you, when you're following along, you don't get confused. So cv2.imread will read in an image into a BGR format from the given file name. Imwrite will write the image to the file name into the format that you specify. Imshow will show the image inside of a CV2 window. You can also pass in a title as demonstrated, and then convert color will convert your image to the encoding that you want to use. Rectangle will draw a rectangle onto the provided image using the top left corner and the bottom right corner passed in as coordinate pairs. And then the fourth variable you see right there is a BGR color value. So in this case, it would correspond to green. And then the last parameter is thickness. All right, and then you can also draw ellipses. Actually, you can draw circles too, and all sorts of other shapes. So you can check out the CV2 documentation depending on what sort of shape you want to draw. But very important for today, we're going to be using the webcam for all of our demonstrations. So in order to activate the webcam, you could call cv2.videoCapture. Most of the time, the webcam that you're using is going to be device 0, so you can pass in that number. And then when you do videoCapture.read, it'll return an error code and also an image representing the frame from the video. And then you can do video capture release once you're done, and then destroy all windows afterwards. And then finally, if you want to label your images, which we'll want to do today, you can use cv2.putText, pass in the image, the label, the starting corner of where you want your caption to be anchored, and then the font and color thickness font size. All right. Cool. So I have a Jupyter notebook located at this GitHub link. I'm also going to paste it in the chat so you guys can clone it. Basically, you guys can follow along. I'll also be coding live on the screen, so you guys should be able to follow along inside of the Jupyter notebook. And we're going to go through a bunch of different functions inside of OpenCV and facial detection tutorials so that you can kind of get familiarized with all sorts of different types of facial detection algorithms out there. Cool. Thank you, Hannah. All right, so assuming you guys have cloned this repo, which also, by the way, contains all the demonstrations for the web scraping and the OpenCV tutorials that we've already gone through today. So that's just a good repo to have it handy. But assuming you've cloned it, then you can CD into the facial folder, which is where we're going to be doing all of our demos. Cool. And if you don't want to install everything manually, you can go ahead and just run pip install requirements.txt. Should have most, if not all of the libraries we're using. Although I think some libraries you might have to still install separately. But you can go ahead and do that. It's not required though. I'll also go through the libraries that you need to install while we walk along. And then please also run /getmodels.sh. You don't need to do it now, but later on we're going to be using certain things downloaded from the internet, which this shell script will collect for us. All right. Okay, can everyone see my screen? Okay, perfect. Cool. So can you guys see my Jupyter notebook? All right, so I have the GitHub clone in this folder right here, and then I'm currently inside of the notebook.ipynb. By the way, so if you haven't used Jupyter notebook inside of VS Code before, go ahead and go into the extensions, install this extension called Jupyter, and then you should be good to go. Basically, that'll allow you to run Jupyter notebooks in VS Code. Also, if you've created your virtual environment in the previous half, go ahead and connect to your virtual environment by selecting select kernel over here, and then you should see your Python environment listed. Just go ahead and select the one that you created. I already have one that I'm going to use, but I will also go through all the installations. So regardless of whatever virtual environment you choose, it should work on your end as well. All right, does anyone have any questions? Okay, cool. I'm assuming everyone could get to this step. So we're gonna get started. So as you know, computer vision is used all over the place, from self-driving cars to signing into your phone and everything in between. So it's very, very valuable, especially facial detection, because faces are one of the primary modes of identification used nowadays. All right, so you already have OpenCV installed from the previous half, but in case if you don't for some reason, or if you joined us late, you can just go ahead and install OpenCV again. The exclamation mark inside of a Jupyter Notebook cell allows you to run shell commands as if you were running them inside of the terminal. So you can go ahead and do this, and then -q will ensure that any output is not going to go onto the screens unless if you want to see it. But in my case, I think it's pretty cluttering, so I'm not going to do that. But let's get started. All right, so inside of the GitHub repo that I sent in the chat, there's a demo image. If you want to make this more interactive and fun and personalized, go ahead and take a picture of yourself right now, save it to the same folder where this notebook is in, name it image.jpg, and you can replace the previous image that was already there. Otherwise, if you don't want to use your own image, you can just use the image that's provided, which I downloaded off the internet, Creative Commons license, and we can run facial detection on it. All right. So we're gonna we're gonna import OpenCV. By the way, it's called CV2 now because actually, yeah, it's called CV2 because there used to actually be a different OpenCV that used C as its backend, but now uses C++. But it has nothing to do with the version of OpenCV, just so you know. Great. So this should work assuming you've installed OpenCV into your environment. We're going to load our image, and then we're going to cv2.imread our image. So now it's going to become a BGR image. All right, and by the way, to run a cell inside of Jupyter Notebook, just press Shift Enter or Shift Return. You can also press this play button next to the cell as well, and it should run. If you're running into any errors, by the way, please paste them in the chat and I can help you as we go along. So as you can see, when we read this image, the size of the image is 4,000 by 2,667 pixels, and then the last column is just the color channels of this image. So we're going to first be doing facial detection. Remember, facial detection is separate from facial recognition. Facial detection just detects a face inside of an image. It doesn't know like whose face it is. And in order to do facial detection, we're just going to use the Har Cascade classifier that I mentioned previously. And so in order to do that, we want to convert our image into grayscale. So we're going to use convert color. Here we have our image. We pass in a CV2 constant, BGR to gray. The other constants are very like intuitively named, so you can think like BGR to RGB or like gray to BGR, etc. So you should be able to guess, but if not, you can always search them up online. So we're going to convert this now into grayscale. As you can see, that took away our third channel because now all of the values have been collapsed into the single dimension of this matrix by taking the average of them. Cool. So we converted our face. And by the way, the face looks like this. We convert it into grayscale. And then now, like I said inside of the slides, we're going to make our cascade classifier. So we use cv2.cascade classifier, and then we pass in cv2.data.har_cascades. This specifies the folder where our pre-trained model, which we're going to use, har cascade dot or underscore frontal face underscore default dot xml. Okay, so essentially this is just a hard cascade classifier that is going to be using pre-trained model weights that should be able to detect frontal faces inside of any image. All right, so let me know if this works for you guys. Cool. So now we'll go ahead and perform the detection. So the way that this classifier works, right, is that you run the classifier using the function detect multiscale on the grayscale image. It works on the grayscale image instead of the RGB image or BGR image because for detecting a face, it's just the color doesn't really matter, and also it saves space when you use a grayscale image. All right, so we're gonna pass in our gray image. And honestly, this is all you need to do. The other fields are optional, but in order to just improve the accuracy, we're gonna pass in some optional fields as well. So you can go ahead and follow me in this case. The scale factor means that we're going to scale down the image by 10%. Min neighbors, as explained over here, is just going to ensure that we're going to delete false positives and only keep like 5 of 5 of the neighboring rectangles for our object. All right, and then finally min size is useful, especially when we're doing facial classification. If you know that most of your images of faces are not going to have very, very tiny faces inside of the image, and this is a very small square, so it's very unlikely that we're going to have a face this size, and so we can just set that min size to save our classifier some space when it's running. All right. Did I misspell something? Oh, I misspelled it over here. Cool. All right. And let's just go ahead and see face is, as you can see, it is a list of faces, and each face is basically a tuple or a list that defines a rectangle. In this case, only one face was detected, which we would expect because there's only one face in the side of this image. So now, given the face that we detected, we're going to go ahead and draw a bounding box. So we're going to unpack our face variable. And so what is inside of this list is the upper left-hand point, and then also the offset in the X and Y directions. And remember that on side of a screen, 0, 0 is in the upper left-hand corner. Okay. So we're going to unpack this. And then we're going to do cv2.rectangle. And then we're going to draw on our image a rectangle with the upper left-hand point at XY, and then the bottom right-hand point at X plus W and Y plus H. And let's go ahead and make the box blue actually, just to spice things up. And then here's the thickness of the box that we're going to draw. So we're now going to be drawing a rectangle on side of our image, specified at these coordinate locations with this color and this thickness. Cool. But you're not going to be able to see it until we do imshow. So first of all, when we display things, I'm going to use matplotlib for displaying our image over here because CV2 also has an imshow function, but that's going to create a separate window. And I just want to display it inside of the Jupyter notebook. So matplotlib uses standard RGB color images. So we're going to convert our image, which is currently a BGR image, right? This is the colored image. We just got the coordinates from the grayscale image. We're going to convert it into an RGB image using the convert color function. And then now we're going to display it using matplotlib. I'm not going to go over too much the matplotlib stuff because this is an OpenCV tutorial, but if you're curious, you can just look at these functions and understand what's going on. Generally, it's just plotting an image with a given size and then showing it. Cool. So as you can see, we drew a blue box around the object that our Har cascade classifier found inside of this image, which is a person's face. And it seems to be working pretty well, although this image was very easy in terms of difficulty, I would say. All right, so that's pretty cool, but I'm sure you guys are like not super impressed because so what, you're just detecting a face in one image? Well, let's go ahead and detect your face now using the webcam. All right, so what we're gonna now need to use is cv2.video capture. So we already have the Har cascade model, so I'm not actually gonna run this, but video capture is going to create basically this webcam object. And on my computer, because I have other cameras installed, my webcam is actually camera number 1, but for you, it should be camera number 0, unless if you have some other cameras installed, in which case fiddle around with it, and you should be able to figure out which camera works for you. All right. Hold on. Okay, I'm gonna keep going with this. Pretty sure that shouldn't be an issue. If it is, we'll figure it out. All right. So first, we're gonna define a function to detect a bounding box inside of a given image. So we're just gonna do what we did previously, but the gist of this is that now with our webcam, we're going to have a live stream of images, and we're going to detect bounding boxes on every single image inside of our live stream. So we're going to be passing, here it says vid, but I should say, I think this looks better with frame because each of these is going to be an image that we're drawing a bounding box on, essentially. All right. So like we did before, we're first going to convert our image to grayscale. Um, all right. And then now we can run our hard cascade classifier on it. Cool. And we should already have our classifier instantiated previously. So I'm just going to reuse it so we don't need to create new things. So we're going to run detect multiscale on our gray image. And then we're going to get the faces out of the image. Or in this case, the face. Cool. I'm not going to put in the other parameters just for simplicity. Okay, so once again, we're going to unpack our faces, and then we're going to draw bounding boxes. So I'm actually just going to copy and paste the code that we previously wrote because it's pretty much exactly the same. All right. And we're going to be drawing it on top of our frame. Cool. And this is not defined. Okay, we'll deal with that in a moment. Personally, I think this should work. All right, so as I stated, this function is going to take in our video frame as an image, and then we are going to draw a rectangle around the face that is detected. So now this code should already be written out for you. The first time, I think it's just good to look at it and understand how it works. So essentially what we're going to do, right, if you remember, the video capture is our webcam, and when we run .read on it, it's going to give us an image that the webcam has just read. But we want continuous images, and so we're going to put it inside of an infinite while loop to continuously read images off of our webcam to simulate the behavior of a video. If you actually want to use a real video, then OpenCV doesn't actually support video, so you have to use libraries like MediaPipe. But I think that this webcam feature is basically good enough. All right, so result is going to be the error code from this. It shouldn't be false, but if it is false, that just means that we didn't succeed in reading an image. And then we're going to run our function on the video frame, get the faces, which let me return the faces here. And then we are going to show now our video frame. So this is cv2.imshow. Previously, we used matplotlib to display an image inside of our Jupyter notebook, but using imshow, it'll just create a separate window that will show the image. And then you don't need to worry about converting from BGR to RGB. All right, and then as we learned in the previous section, wait key is just gonna wait for 1 millisecond and then check if you press the Q key, and if you did, then it'll destroy the window. Once we demonstrate, I think it'll be easier to understand. Also, there's one thing I forgot to write over here. You should also put cv2.wait key after anytime you call destroy all windows. That just ensures that there's enough time for it to process that command and that it destroys the windows properly. All right, let's see if this works out. Okay. So sometimes, especially when I'm doing this over Zoom, my computer gets a little bit laggy. So, and that might happen to you as well. So I just recommend restarting your kernel. and then you can rerun things, and usually that clears things up. Oh, there we go. Oh, I fixed it, and that's why it was not working. Okay, but we'll just re-import OpenCV, and honestly, I think you just need to rerun the face classifier line. Right. And then we're going to turn on our webcam. Great, so this time it worked out. So sometimes you just have to restart your kernel. By the way, is everyone good so far? If you have any questions, please paste them in the chat. All right, and then we're going to do this function, and then we're going to do this infinite loop to basically turn on our webcam. So let's go ahead and look how it looks. So as you can see, it's detecting my face inside of the video frame. How this is working is actually, it looks like a video, but it's just running really, really fast and displaying images from my webcam. And then you can see the pre-trained model is pretty good at detecting my face, but sometimes it detects my eyeball or like other parts of the image that are not really relevant. So this you can kind of fix by adding those other parameters that I didn't add this time. But even then, hard cascades is just a hard-coded model, and so it's not as good as like deep learning models that we're gonna actually play around with next. So once you're done with this and you've had some fun, just press Q and it should close itself. Great. All right. Did it work for everyone? All right, great, awesome. And like I said, like you guys probably will have to say like, device 0, unless you also have your webcam being device 1. And you'll notice that when you run this. All right, cool. So let me go back to the slides really quick, because now we're going to talk about some deep learning models that are used nowadays, since hard cascades classification is pretty outdated since it's from 2001. All right, so the most powerful deep learning model in the world right now is the YOLO classifier, also known as the you only look once classifier. And when I said, oops, most powerful, I'm just talking about for object detection. So if you have heard of the COCO dataset, it's this dataset of 80 different objects, like humans, cats, dogs, all sorts of different, okay, I shouldn't, okay, sorry, I don't mean to say objects in that sense, but 80 different like labels or classes. And it has just a bunch of training data, and it's available on Kaggle. And if you want to create the next great object detection algorithm, you can go ahead and submit your code, and maybe everyone will be using your model next. But I'm just going to demonstrate or explain really briefly what YOLO is. Um, so actually, there's many different versions of YOLO. YOLO version 9 is the latest one. I think it came out in February. And it's just really good at detecting objects. And remember, object detection is where we draw a bounding box around the object, whereas like other sorts of computer vision tasks like segmentation will actually like draw the outlines of the object, but we're specifically looking for bounding boxes. So it's a convolutional neural network. It's in um, the one-shot family. And basically the way that it works, and if you want to go into more detail, I also recommend, going to ACM AI and learning more about like a lot of different deep learning architectures. Um, but it'll essentially split the image into a bunch of different boxes and then draw bounding boxes with different confidence intervals of whether or not the object in that image corresponds to a specific class. And then areas with high confidence are going to be labeled as detected objects in one of the 80 classes, or however many classes the model is trained on. So as you can see, there are a lot of different models that are used nowadays for like really high accuracy object detection. This is going to be also more computationally expensive to run, but YOLO generally is like one of the top algorithms out there. And today we're actually going to be using YOLO version 3 just because it's been around long enough that there's a lot of API support for it and pre-trained models that we can go ahead and use it for our data set. So yes, there you go. Any questions so far? All right, cool. So I'm going to break out of this and then go back into our VS Code. So can everyone still see my screen? Awesome. All right. So basically, over here inside the notebook, if you weren't following along, it kind of explains what I just said, where what YOLO is, the architecture that it uses, and why, it might be something that you want to check out. So the thing about YOLO is that as like a very large deep learning model with like a lot of weights, you're gonna have to load these weights separately. So there's a shell script inside of the repo that you clone. You can just go ahead and run it get models.sh right here. This is what it looks like. All it's doing is downloading these files from these different links. The reason why I didn't just put those files inside of the GitHub was because they're very large, so they can't really, you wouldn't have been able to download them fast. So if you don't have these, and you probably don't right now, just go ahead and run .get models.sh. I mean, I'll just go ahead and run it again, I guess. But actually, it'll probably take some time. So I'll actually not run that. But yeah, so while you're running that, let's go ahead and walk through the code. So some of this I've already written out here because this is really implementation specific. So YOLO, as its backbone, uses this large deep learning model called darknet. And so OpenCV is really great in that it basically has like APIs for anything and everything that you could ever want. So darknet is also in here. You're just going to load in these configurations, and then you're going to get our YOLO model, essentially. And then these weights are specific to the Cocoa dataset that YOLO was trained on. So we're going to be using the Cocoa dataset. So in other words, we're creating a model that actually is able to detect like 80 different types of objects. And so this strays a little bit away from facial detection, because actually face is not one of the objects, instead person is, but it should still be able to detect you inside of the image. And if you are lucky enough, you will also be able to see how it's able to detect not only that, but also other things. All right, so just can everyone give me a thumbs up when you've been able to successfully run .getModels.sh or /getModels.sh, or is anyone having issues with that? You can also manually run each of these lines of code inside of the same directory where this notebook is stored. Okay, so I don't see any reactions from anyone, but if you are still just waiting for it to download, I'm just going to go ahead and just briefly explain what's going on over here. So the cocoa.names is actually just a text file that contains the different classes that are inside the Cocoa dataset. So we're just going to read those into our, a labels array over here. And then just to set up the model, we're going to need to run these specific functions. I'm not going to like explain too much into detail how these work, but you're just initializing the input and output layers. And it's called YOLO v3 partially because there's actually 3 output layers depending on the image size. Cool, so now let's go back to OpenCV stuff. So we're going to get our image, which we can just do using cv2.imread. And you can just use the previous image that we were using. Honestly, it should work, but you can use whatever image you want as well, right? And then we're going to resize the image into the size that the network accepts, because this network actually only accepts square images that are 416 by 416 pixels. So luckily enough, the deep learning module or deep neural network module inside of CV2 has this cool little function called blob from image, which will just select the right input crop from the image that you want to pass in. All right, so we can go ahead and run this, and then we can initialize our network and then do forward passes on the network. And then now that is basically run our model. Cool. So I've provided all this code here because there's a lot that goes on since we have 80 different class names, but I'll just briefly explain how this works. All right, so on a high level overview, just like the hard cascades model that we were using previously, this model is going to be providing us bounding boxes for the different objects that are detected in the image. But unlike the hard cascades model, which only provides us bounding boxes, this model actually is classifying different objects as different objects, basically. So it's also going to be providing us class IDs. So that's just this additional list that we have over here. And then if you wanted to analyze the confidence scores, you can also get those. So any questions so far? I know this is a lot. Also, sorry, I think I may have drank too much caffeine today. If I'm talking really fast, I can slow down a little bit. But yeah, there's a lot in store. I hope you guys I'm sure you guys will enjoy what's gonna come soon. So as I mentioned, there's actually 3 outputs from this model, one for each scale. And the way that it works is we're just gonna determine the confidences from all of them, average them, and then pick the one that's the highest. So in each of the output, there's going to be multiple different objects that are detected. And then it just so happens that inside of this detection list, the confidence scores are also stored in the exact same thing, but basically from the 5th index onward. So this is just really specific to YOLO. And so like this isn't really something that you should memorize, but whichever model that you end up trying to use for OpenCV, you should just search up specifically how the output is formatted so you can extract what you need. All right. So we're going to select the class that had the highest confidence score and then append that confidence score to our output in case if we want to view that later on. And we're only going to consider objects that were predicted to be that specific object with a confidence of at least 50%. All right, and then basically detection 0, 1, 2, 3 is what we just had before, like X, Y, W, H. We're just going to be rescaling it to draw on our image. All right. And then here's a function to remove overlapping bounding boxes. So I'm going to run this. And then the reason why we imported NumPy. So by the way, if you don't have NumPy installed, go ahead and just run pip install NumPy. And that should get NumPy installed for you. But most of the time, that's already installed. So we're actually just using it to generate random colors for each of the different types of objects that we detected. So it's not that big of a deal. If you don't want to use NumPy, you can just manually encode the colors. But we'll go ahead and select all the bounding boxes that are kept after non-max suppression. And then we're going to draw it using cv2.rectangle. So once again, we're just going to be putting in the upper left-hand corner, the bottom right-hand corner, the color, which in this case was generated randomly using a uniform distribution over 0, 20, 20, 255, and then the number of classes that we have. Those are the different amounts of objects that we're going to select. All right. And then our thickness of our rectangles is going to be 2. And then we're going to use the put text function as we mentioned in the slides. So we're just going to be drawing a caption onto the image, and then with this specific text using an F string to basically put in what class this object was determined to be. Also, its confidence score formatted as a float with 2 decimal places. And then we are going to tell it to put our label at x, y minus 5, which is basically the upper left-hand corner of the bounding box, but then we're also moving up by 5 pixels so that we have enough space to see the text without it overlapping with the bounding box. And then we're also going to use this font. You can use whatever font you want, but this is just the standard one. And then font size, color, and thickness. All right, and then we're going to use cv2.imshow. So this is going to create a new window to destroy our window. In this case, wait key 0, I believe, will just allow you to automatically destroy the window whenever you press any key. So let's go ahead and test it out. Hold on, I think my thing is loading. Great. Can you guys see my screen? Awesome. Okay, so look at this image. Basically, it detected there was a person and also detected a tie because a tie is apparently one of the other 80 classes inside of the Coco dataset. And these are the confidences. It was 100% sure this is a person, and then it was like 93% sure that this is a tie. So this is just an example of what you can basically do. So using object detection, you'll get these bounding boxes of objects inside your image. And then once you get the crop bounding box of the object, it's really simple to pass that into a regular machine learning model to determine like what that object is using classification. Does that make sense to everyone? All right, awesome, great. So let's just press Q and it should delete itself. And it is loading. I'm sorry, this is like kind of slow. Eventually it should delete itself. If not, oh, I think I forgot to put this wait key 1 after destroy all windows. That normally ensures that it will delete itself. Great, cool, perfect. Did anyone have any issues so far with this part of the demonstration? Is everyone following along okay? If not, you can unmute yourself or like send something in the chat. Cool. So now we're just going to go ahead and do the same thing that we do with the hard cascade classifier, which is we're going to set this up with the webcam and basically emulate a live stream video to see how it works. All right. So once again, I'm not going to ask you guys to type all of this out because this is just copy and paste of what we did previously, but put inside of a function to operate on a specific frame of a video. All right. And then we're going to initialize our webcam. And then now we're going to make our infinite while loop, right? And this should be basically the same as what we did previously. So we're going to get our video frame out of the webcam by calling the read function on our webcam. And then, oops, my thing is so slow. All right, I'm waiting for it to move to the next line. In the meantime, you guys can keep on following along. I know that the SH script might have taken a while, so take this time to catch up or take a break if you need one. All right, cool. It succeeded in entering. So as previously, you know, if our error key is actually true and we had an error, then you're not going to want to display this image because that just means that the image wasn't read. We're going to run our same function, which we call detect bounding boxes. And that's just going to give us the same thing as previously, which is the rectangles representing our objects. In this case, it's not faces anymore, right? Because actually, we loaded our YOLO model with the Coco dataset, so it's able to not just detect people, but also everything else inside of the Coco dataset. Cool. And then we're going to use imshow, and I'm just going to say YOLO v3 model output, right? And we're going to display our video frame. And then the way that we break out of this while loop is just, okay, give me a second. My VS Code is getting laggy. Okay. I think it might be that my enter key is broken. Oh, there we go. Okay, great. And then we'll just break out of this if wait key equals 1. And then we're gonna just check that the value of the wait key is gonna be Q. That's gonna be the key that we're gonna use to break out. Then we'll break out of this infinite while loop. And another thing is that if you ever get lost and I'm going too fast, or too slow, you can always check the notebook underscore answers dot IPYNB, and it should have all of the code that you can just run on your own. Cool. There we go. All right. Wow. This is why some people like indenting in languages, but it's also nice to be able to use semicolons. Okay. So at the end, we're going to release our webcam, and then we're going to run cv2.destroy all windows to destroy the windows. And then, as previously, don't forget to also put cv2.waitkey1 after you run destroy all windows to ensure that it waits long enough to register that you press Q. All right. Maybe I'm gonna like stop sharing screen and reshare if that's, oh, okay, there we go. So cool. All right, so let's go ahead and run this. What this should do, if everything was typed correctly, is do what we previously were doing with our hard cascade model, which is running it on side of a live stream of video feed, but instead now we're going to be using YOLO. So let's check it out. Oh, CV2 has no attribute wait key. Oh yeah, I'm sorry. Should be capitalized. All right, let's run it again. Okay, it might take some time. Sometimes, like I said, you might have to restart your kernel if there's a lot of things that just get cluttered inside of the kernel memory. Oh, wait a second. No, I was wrong. It was working the whole time. I was just not paying attention. So as you can see, it's running the live webcam on me, and oh, I'm also home, by the way. But it can also detect that this is my Android phone. Should be able to detect that, and all sorts of other things. But I'm not going to go into too much detail, so it's pretty sure that I'm a person. So I'm just going to click Q, and then we're going to go back into the code. All right. It's pretty laggy right now, so it might take some time to register. If it doesn't register, just keep pressing Q and it should eventually break up. And if it doesn't, I'll just restart my kernel. And that's what you can do as well. Okay. I'm not sure how long it'll take before. If you have noticed, by the way, this is much more laggy than when I was using hard cascades because, the model is just much more large, and also it's detecting 80 different objects at the same time. So that's another reason, but just in general, like hard cascades is very, very lightweight and efficient, and so that's why it's good to know, despite the fact that it is just a standard non-deep learning model. Cool. So was everyone able to get that to work and have some fun with facial detection? All right. If not, please once again unmute yourself or say something in the chat. Otherwise, I have no idea. And I'm just gonna keep going because there's a lot more cool things that we're gonna get to. So I hope you're as excited as me. Cool. See, it destroyed itself. So eventually it did register that I pressed Q, which is great. All right, let's get back to the agenda. So now we're gonna do emotion recognition, but before we talk about emotion recognition, I actually want to give a content warning that emotion recognition is one of the controversial aspects of artificial intelligence. So for example, the EU has like banned certain uses of emotion recognition, and a lot of people basically say it's pseudoscience, which it basically is, but so please don't take the output of emotion recognition as actually being able to read your emotions, because it's just being able to read a certain facial expression and not necessarily what you're actually feeling. So please take it with a grain of salt. But if you're interested, we're going to be using this library called FIR, which stands for facial expression recognition, which has essentially open source pre-trained models on facial expression recognition. And it uses the hard cascade classifier underneath in order to detect the bounding box of your face. So that's just how widely used this hard cascade classifier is. If you want, there's actually an alternative where you can specify to use an MTCNN model to do so. But for some reason in my environment, sometimes it breaks. So I'm just going to use the hard cascade classifier. All right, so let's go ahead and do that. Right back in our notebook, right? Everything should be in our notebook. All right, can everyone see my screen once again? Okay, perfect. Cool. So emotion recognition with OpenCV. So this is just another example of like OpenCV, very often you're not going to just use it by itself. You're going to like, depending on what specific problem statement that you're trying to work on, you might use some other library that's specifically designed for that specific problem statement and then use the functions of OpenCV in order to like read images, convert them into different encodings, and etc. Okay, so we're just going to import all of these different libraries. By the way, you probably don't have some of them installed, so go ahead and just run this. Also, you want to install facial emotion recognition and image IO. And I believe the other ones you should normally have installed already. So you can just run this inside of your environment. If you have any issues, please let me know. Alrighty, let's go ahead and go ahead. So you don't need to worry about this. I'll explain this in a second, but don't worry about it for now. All right, so we're going to import our libraries. Some of these, by the way, we already imported, so it's kind of redundant. But if you were just running this separately, if you're only interested in a specific part of the notebook, that's why I wrote them, so that you import the libraries again every single time. All right. So how we're going to do this is we are going to initialize our facial emotion recognition detector model. And under the hood, this is just using hard cascade classifiers to identify faces inside of an image and then run expression recognition on the image. So I should change this to expression labels. These are the different expressions that this model was trained to capture. You can also copy and paste this from notebook answers document. Cool. And then, as I previously said, you can also set MTCNN equals true to use a different backend in order to detect the faces inside of your image. But I've just found that it crashes my kernel sometimes. Using hard cascade is much more lightweight. So I'm just going to just go ahead and go with the default model, which is what we used previously. All right. And every time we want to do some video capture, we have to re-instantiate our webcam because we previously closed it. So we have to make it again. All right, so we'll turn on webcam and then I'm going to, for this part, there's some things that you can just copy and paste for now. So I'm just going to go ahead and grab those. Because right here, we will be creating, we're going to be detecting emotions inside of a live webcam feed of yourself. So we're also going to be saving that live stream into a video file, an AVI format in particular. And so actually we also need to say our frame rate just should be 4.3. Cool. And image.io, like I previously said, inside of the slides is a great library in order to create and read images. If you're not going to be running any sort of specific transformations on them. So in this case, we're just going to be creating a GIF or GIF. Ooh. Okay, so sometimes when you run into errors like these, it's probably caused by your kernel getting overloaded. So let's go ahead and restart the kernel actually. And in the meantime, because currently my Jupyter notebook is getting laggy, let me actually just show you something fun to give you a taste of what we're trying to do here. And actually, it's, in my opinion, better than what we're able to do inside of a Jupyter notebook environment. This tutorial, by the way, credits to a specific website where I basically got this tutorial from. But you can obviously, it's obviously, customize it a little bit, and you can customize it for your own needs. All right. So while we wait for my kernel to fix itself, there's another script that you should have inside of your GitHub folder that you cloned, right? It's called emotion.py, and that is basically what these lines of code are, but just neatly formatted into a Python script. So you can just run that script using /emotion.py, and it should be able to give you a live webcam feed of different expressions that are recognized on your face. And so I'm just going to be explaining how this works. So like if I pretend to be happy, then it should be able to detect my face. Or like if I'm sad, then it should also be able to detect it. And it also has this live bar chart, which shows you the different percentages of your expressions that it detects. Now, the reason why we can't do this inside of Jupyter Notebook is because Jupyter Notebook has specific like restrictions on the number of threads you can run. And so because this is simultaneously using OpenCV's webcam and also doing this live window, it doesn't work in Jupyter Notebook, unfortunately. So that's why I provided the Python script if you want to get the full features. But we can just go ahead and press Q. This should close itself after some time. And we're going to try to get this to at least work partially inside of our Jupyter Notebook. Was everyone able to run the Python script on their own? You may need to install TensorFlow as well in the backend. And I'm gonna go ahead and rerun this. All right, give me 1 second. All right, so it's saying that fur is not defined. So if you're not able to import it, just install it using pip install. Cool, now it works. And oh, but we need to install the other things. Try that. Interesting. Why is this giving me this error? There we go. All right, so if you had any issues, once again, paste them in the chat because that way I can help you with that. So, sorry. Cool, so we're just gonna put this in our Jupyter notebook. I'm just gonna explain how this works because it's a little bit complex because we're also trying to generate a graph and also a video at the same time. So right here, we have a function which updates our bar chart for every single frame. And remember, we're going to be detecting emotions for every frame in the video. So we're going to be calling this function for every frame of the video and plotting the appropriate statistics onto our bar chart. I won't go into too much detail once again because we're focused on oops, I went down too far. OpenCV and not matplotlib. All right. So you can run this, should do the same thing that we did with our Python script. Oops, I think I might have forgotten one thing. Or I may have forgotten to run it. Yes. It's because the name was incorrect. All right, there we go. So it is detecting my motions once again. The bar chart is not being displayed because, like I said, in Jupyter Notebook, you can only display one window at a time. But go ahead and test this out and see if you can like trigger the different expressions that it's trained on. As you can see, this is just in general using facial detection or object detection. We get a cropped region in our image that we can do any sort of machine learning thing on it. So whether that be classifying expressions or classifying objects or even more, which we will soon see. All right, so you can press Q when you're done. Should eventually close. All right. How's everyone? Do you guys need a break? Are you guys good? I know that we went through a lot so far. And just want to take a rain check on how things are going. Is everyone following along okay? Okay. I'm just gonna drink some water and then we'll get moving on to the next part. Okay, cool. So finally, one of the things that maybe all of you are waiting for, or some of you may have been waiting for, is facial recognition. Because I mean, facial recognition is like perhaps the one of the like name like well-known things of computer vision, and your like computer uses it to sign you in perhaps, or your phone, or apparently now the TSA uses it, and so it's used for like so many different things. So we're just gonna go and explore how this all works and then implement it ourselves. Does that sound good to everyone? Great, let's do it. All right, so facial recognition. Like I said previously, what we're using is we're just using this very basic hard cascades model, or maybe if you want to use like MTCNN or something else to detect faces in an image, you can go ahead and do that. And then once we get our faces, they are cropped out of the image and then passed into a facial recognition model, which classifies them into different types of, in this case, which face corresponds to which person. All right, so OpenCV. OpenCV is so amazing. It has everything you need, including a regular machine learning model to classify faces into different, like, basically you can train your own model to classify faces as different people. And this is called the local binary pattern histograms model. And it's very, very simple. It's not even a deep learning model. All it does is it takes the cropped image of a face, and then it kind of assigns this mask to it. The lighter regions of the mask are assigned higher weight because they are used for, I guess, the model to differentiate. And then it'll essentially use some sort of like similarity, whether it's like, KNN, or let me move to this slide. Okay, it's not written on the slides, but in the back end, it's just using something like KNN, for example, to determine the similarity between an input face that it gets with the encodings that it got out of the training data. All right. Does that sound good to everyone? Cool. Okay, so OpenCV, what functions we're going to use? Basically, once again, our face cascade, which we already defined previously, which we just use, cascade classifier to make our hard cascade. We're going to get the faces in the image, the grayscale image, remember? Then, for every face that we detect, and you might detect multiple faces if you have an image with multiple people, but that just depends on your image. Then we're going to get the specific segment of the image that your face is inside. We can just go ahead and use this crop that uses the X, Y, WH in order to crop it out of the image. We're going to append the face to our list of faces and then feed these faces into cv2.face dot lbph face recognizer underscore create. So CV2 has an entire sub-library called face just dedicated to all the different functions you would ever need to you do face still detection recognition or anything else related to faces. And so it's really, really a great library. So we're going to be using this API essentially to do just that. All right. Oh yeah, and there's other facial recognition algorithms, by the way, which we will at the very end do one last time. All right, so let's do this. Okay, so once again, make our imports. And then, okay, I think some of this I forgot to delete, but as you should have already previously learned, right? To create our face classifier, we're just going to use cv2 dot cascade classifiers classifier, and then cv2 dot data dot r cascade plus cv2 dot what was I going to say? No, it's going to say the frontal face dot xml. I think I might have typed this a little bit wrong. Let me double check. Oh yeah, har cascades and har cascade underscore frontal face default. Okay, but essentially that's the format of how this works. And then we're also going to make our face recognizer. We're just going to operate on top of the cropped images that we got out of our facial detection model. Okay, cool. Let's go ahead and do it. Hopefully my kernel doesn't need to be restarted. It's taking a little bit. Anyways, let's also explain what's going to happen next. So, essentially, just like we did previously, we are going to, uh-oh. I think my kernel might be a little bit broken. So let's just try that again. Great. Hmm. All right, give me a second to debug this, guys. Okay, I think I'm gonna. Is anyone else having the same issue, by the way? No. Okay, it's great. Well, okay, then we can skip to the next part while I try to fix this. So don't worry, we're still gonna do facial recognition. But instead, well, let's go ahead and just jump straight into the deep learning version, because what we were gonna do just now was LBHP, which is not even deep learning anyways. So, I guess it doesn't work, but that's fine. Um, we'll do the better one. All right, cool. Deep learning models. Install these libraries, please. Um, the DLIB has like a lot of cool deep learning models and functions that you can use in a lot of different applications. Face recognition is one of these like um, case specific libraries that is really great for doing deep learning powered facial recognition. So we're just gonna go ahead and install those. I actually already installed them, but you can run this. Cool. All right. And now for the fun part. So inside of this folder, inside of your folder is another subfolder called people. And you can put all sorts of images in here. I put an image of myself and also Stephen Curry. I think inside of the GitHub, I put an image of just the example image from Creative Commons. But if you have an image of yourself, drop it into the folder. You can use it to train a facial recognition model. And if you have images of other people that you have permission to use, you can try that as well. All right. So let me explain what's going on here. So we already know we've done the webcam so many times already. We know what we're doing over here. But face recognition is gonna load in this image and then it's going to extract encodings off of this image. Um, don't ask me specifically what the encodings are. I'm not exactly sure. But essentially it's going to get encodings and then determine the similarity of whatever image that it receives that it doesn't know about and compare it to the encodings that it knows about and then classify you to the nearest one, if that makes sense to everyone. That's also kind of how like actually a lot of like ChatGPT and everything else works is just comparing to known encodings and picking the one that is most similar. All right, so we're gonna run this. Basically, I'm just gonna instantiate my model to know who I am and also who Stephen Curry is. And if you want to add more people, you can do that too. So my name is Sam. You can insert your own name or whoever's face you decided to put in there. All right. And then the same model, once again, because we're using the webcam. And honestly, the webcam is really, really cool because in this case, we're using a computer, but what if, for example, you had an embedded device and you wanted to create an application to, for example, detect squirrels and like do certain things based off of whether or not they're present. And don't ask me where I got that idea from, but you would just basically do this. Have a while loop where you're reading from the webcam and it would work inside of whatever device you have as long as it has a camera. Cool, so we have our while loop. Once again, we're gonna get our image frame. This time we're gonna make it smaller. You actually don't need to do this, but it'll just make things faster for our model. Once again, we're converting from BGR to RGB because face recognition is not part of OpenCV, and so it uses regular RGB images. And then process this frame is set to true. And we are going to get, first of all, the bounding boxes of the faces in our image. And then we are going to get the encodings out of those bounding boxes. And then we are going to compare this encoding that we got from this unknown face with the ones that we already know about. And then if they are similar enough, then we will determine what class that face belongs to, and then we're going to append it to this names and then display it on the screen using, once again, cv2.putText. So I'm repeating myself a lot here because we're just reusing so many of these OpenCV functions. But let's just go ahead and run this. So yeah, it knows it's me, but you know, that's kind of self-explanatory. Let me see if it also knows Steph Curry. So I'm gonna get Steph Curry over. All right, so I have a picture of him. Boom, and it knows that this is Steph Curry just from one image, by the way. So that's just like the amazing power of like some of these new deep learning models that you can use through these libraries. Awesome. All right, and then just press Q to quit. And I forgot to put cv2.wait key 1. Oh man. So I'm gonna have to run this again to press Q again so this goes away. But hopefully you were smart enough and caught that. And if you didn't, just run it again. It's no worries. And that's basically the end of today's tutorial. Oh, interesting. Well, it just worked out. So I'm gonna stop sharing my screen and open the room for any questions that anybody might have, as well as like if anyone wants to share what they built or what they tried out. If you were able to get the non-deep learning facial recognition model to work, that one you can actually train on yourself. And if you have like anybody else with you that you want to take images of, it'll automatically take images of them. So it's pretty cool. But yeah, any questions, anybody? Wow, everyone understood everything, huh? I'm so happy that you guys are like so great listeners, and thank you so much. And let me just close out the presentation. So now you know how facial recognition works. We just get a bounding box, then do regular machine learning on it. And if you want to view the sources and do things on your own, there's awesome tutorials in here as well that you can check out. They all use OpenCV, so it's a great library. You should use it. Thank you so much, everyone. Thank you for coming.
And thank you guys who came to both of our workshops too. I hope that you thought they were as incredible as I did. Officers really crushed it with the curriculum. So yeah, these recordings will be posted at some point, hopefully soon, if you want to go back and try things for yourself. Also, you have the links to the GitHub and the slides, so you can go and try some other stuff too. Python's a pretty amazing language with a lot of things that you can do. And it is a shame that it's not taught as deeply as I think I was expecting when I was coming to college. So I hope that you found this useful and had some fun while you were doing it. So yeah, so thank you all so much again. Hope you enjoyed.